Okay, so when we have a B plus tree and we plan to do some queries, and the query process actually matches the searching process in the index tables. Remember before we mentioned we have different queries, right? Either equivalent query or some range queries. Now here we provide you with the example. We want to select name, this attribute, from people, this table, where age equals to 25. And here let's assume we have an index table created for this age as such key. If we have some queries like this, and how can we do the search process to find records matching this condition? Normally you can imagine we start from the root and we proceed down, matching the key values versus this provided value, right? Decide which branch to go to until we reach the leaf. And in the leaf, we still find if we can find some tuples matching this record, right, with 25 as age, and then we can access the concrete tuples and return the name attribute of a tuple. This is the equality queries, right? The search process in the index tree. And the query for some range queries, it will be very different. Now here we have an example. We select name from people where age is no greater than 20, where the age is no smaller than 20 and no greater than 30, in the range from 20 to 30. And how can we do this search in the next step to find some concrete tuples matching this condition? The beginning part is very simple, right? It's very similar. We start from the root, proceed down, and we match the records with the number 20 as an example. Right? And if we can find some tuples whose age is no smaller than 20, and then we can do the sequential traversal. Because remember, for the leaf node, we have this pointer, right, pointing to the right-hand side, the leaf node. In other words, if we can find some tuples, we matching our condition, we can just go right to find some more tuples whose value is larger than the current value, right? And we can do a sequential traversal. And we can access until this age is greater than 30, and we will return all the tuples we have reached in the traversal process. And we can provide you with an example within the B plus tree. And let's say we create a B plus tree and we specify the D parameter to be 2. I always still remember this parameter, right? This D means all the key numbers in each node should be in the range from D to 2D. In this example, the number of keys in each node should be in the range from 2 to 4. Right? We have an exception, it is for the root. The root is the exception where now it contains only one single key inside it. And we create an index table with about the ages of the person. And the root will have one value, which is 80. It has 2 pointers, one pointing to the left-hand side, one pointing to the right-hand side. Inside it, we have so many entries which are blank. It is a node, and it is also legal. And to the left-hand side, we have one children node. It's also the internal node. Inside it, we have 2 keys. One is 20, one is 60. It's a node, right? Because the D value is in the range from 2 to 4. We have 2 keys. It's a node. And we have 3 pointers. The left pointer pointing to a children node, whose value is in the range from 10 to 20. And this pointer between 20 to 60 is also pointing to a children node. The key value in the children node is also in the range from 20 to 60. And this right pointer points to a children node. The value inside the children node is larger than 60. Remember, here we have 80, right? In other words, all the key values inside the children node should be from some values to 80, right? The maximum value will be 80. Similar for this one, right? The largest value will be in the range from 60 to 80, actually. It will be similar for this children node, right? On the right-hand side, all the values inside this children value should be larger than 80, right? And we also have 3 keys for this children node, 100, 120, and 140. And left hand, and the left pointer pointing to a children node, the value range in this one should be between 80, right? Because this one is between 80, right? Because this one is larger than 80. In other words, this value in this children node should be from 80 to 100, and so forth. And the nodes in this level, they are all the different nodes, right? And inside it, we also have the keys. Now in this one, we have 3 keys, 10, 15, 18, and we also have pointers. The left pointer points to a tuple with such key value equals to 10, matching this key value. This one have a tuple with key value matching this 15. This one have one tuple matching 18. These are the concrete tuples stored in our database tables. So this part is the index table. And the bottom part is the concrete tuples stored in our database system. So they are very different, right? This is index table. These are tuples. And this one denotes the pointer pointing to some tuples we store in our database systems. And this one is a tuple with 18 as the key values. And this one, in these 2 entries are blank. However, for the right hand side is pointer, they're pointing to the next children node, the next leaf node, right? And for this one, we have the records matching 20, matching 30, 40, 50, etc., and so forth. So here, if we plan to do a search with the age value equals to 30, how can we do the search? We go from the root, right? We check this provided value 30 versus this key value. We find 30 is less than 80, right? Therefore, we have to go to the next branch. And we compare 30 with the key values. 30 is larger than 20, smaller than 60, right? Therefore, we have to go to this pointer and going down. And we'll compare the 30 versus all the key values inside the children node, right? 20, 30, 40, 50. And we find one tuple matching our value, right? 30. Therefore, we will access the pointer pointing to the concrete tuples matching our requirements or the values. And from this record, we can access the attribute, the name of a person, right? And we also return the name of the person as a result. So this is such a process for the equality queries. If we have some query now the condition is where the age is not smaller than 30, how can we do the search? We want to find some tuples whose age of a person is not smaller than 30, right? How can we find these tuples and also find the name of this person? The search process is very similar. We also use the 30 as a key value for comparison. Starting from the 80, from the root, we compare, go to the left, and go to the right hand side, and we can access the tuples, the value matching 30, right? We'll access this tuple, also give the name. Remember the condition we have is age is no smaller than 30. In other words, we can further go right hand side because we can ensure all the values on the right hand side are larger than 30, right? Because each node is sorted. And from this pointer, we further go to right hand side. We access this tuple as well, 40, this tuple as well, 50. And if we finish this node, remember we have a pointer pointing to the next leaf node, right? In other words, we don't have to access from root again and go to this node. We can directly going from this node to the right hand side to this node. We access the tuple with the age which is 60, 65, 80, further go to this node, 85, 90, and further go to the right hand side. In other words, for the range queries, we can find the first entry matching our requirements, and we can further do the traversal to the right hand side to get all the tuples matching our requirements. Okay, so this is a search process in the B+tree. I hope you can follow me, right? And you can also try to do this search process by yourself by drawing down on paper. You can have a deeper understanding about search process in the B+tree. Okay, so this is about the example. Remember before we mentioned that the B+tree have one parameter, which is D. The D parameter is very important. Normally D controls the shape and with the structure of the B plus tree. And when we design a B plus tree at the index table, we have to specify the D value, this parameter. And you may wonder how large this D value can be. Remember, this D controls how many kids we can have for each node, right? So if a D parameter is very small, what will it mean? If D is very small, it means each node will contain a very small number of keys, right? Inside it. What will happen? If we have a very small D, given an index table, if we have many records to put in this B plus tree, then the B plus tree will create for its a small D will be very deep, right? If the D is very small, we have to build a very deep B plus tree instead. Then it will have some problems, because if we have a very deep B plus tree, remember before we do the search process, we have to start from the root and going to these leaf nodes. If this B plus tree is very deep, in other words, the process from the root to the records will take lots of time. And how about D which is very large? If the D is very large, it means this B plus tree will be very flat, right? Because we can contain so many keys in each node. If this D is very large, in other words, these nodes can be very big, right? We have so many pointers pointing to different tuples, and the tree will be in a very shallow structure. It can reduce the time cost. We do this from the root to the tuple process, right? It can save lots of time. However, can we use a very large D? The answer is no, right? Because when we create an index table, we have to store it in a storage space, like in our hard drive. However, if you still remember, for some disk, right, for the hard drive, we have some size for each of the block. Now, for some systems, we have a block size which will be 4K bytes, right? And we have a limitation for the block. Normally, for convenience in accessing the data, we plan to store the node in one single block, right? We don't want to divide one node into several blocks instead. It will create some problems. In other words, the maximum size for a node should be smaller than one block, right? And we have a limited size we are now for each of the D. And to store B plus nodes in one single block, in other words, the D size will be limited. The main reason is because if we plan to store the B plus tree, and we have to allocate the space for both the keys and the pointers. Now, for the keys, we can assign a space with 4 bytes. For pointers, we have assigned a space with 8 bytes, right? Remember the D value, right? Given a D value, the maximum key values we are now for each of these nodes will be 2D, right? You still remember the range, right? It's from D to the 2D. In other words, the largest number of key numbers we are now for each node will be 2D, right? And larger number of pointers for each of the nodes will be 2D plus 1, right? Right. Now this one, we have 2D as the maximum key value allowed for the nodes. Inside, the maximum number of keys we have will be 2D, right? And pointers is always larger than these are keys with 1 extra pointer, right? So therefore, the space we can use for storing the B plus tree will be, the maximum space we can use will be 2D times 4, right? It's for storing the keys, plus 2D plus 1 times 8 is for storing the pointers. It should not exceed the block size. It is no greater than the 4K bytes, right? In other words, D value should be no greater than 170. We have a limited size for D value, right? This is the maximum number we can allow for the D value for creating a B plus tree. And normally in the real world application for the B plus tree, normally we don't use the largest number, and we can use a small number instead. So typical order for the B plus tree will be about 100. Remember that in B plus tree we can have some blank entries, and the typical fear factor for the B plus tree will be about the 67%, right? As to the pointers we have for the nodes, the average fan out will be about 133. In other words, we still have some pointers and the key entries which are blank in the B+tree's nodes. This is very healthy because later we will show you about how to insert delete for the B+tree. If we have some blank entries there, it can provide us with some flexibility for inserting new tuples into the B+tree. In other words, this thing out as well the feed factors, they are very healthy for the B+tree. And based on these typical numbers, the capacity we can store for the B+tree, if we have a tree with 4 depths, and the maximum number of records we can store in the B+tree will be about 133 raised to 4, right? In other words, this B+tree can refer to the maximum number of about 312 million records. And we can create so many pointers pointing to this number of records for some tuples. If we have a B+tree with 3 layers, then the maximum pointers we can point into tuples with about 2 million records. Normally, this size should be sufficient for us if we don't have a very large system to run. However, if we have a very large system like the Amazon or Facebook, and this number can still be very small, and they have to build a larger B+tree instead. If we have a B+tree, normally we prefer to hold the top levels of the B+tree in a buffer pool because we have to use these top layers very often and frequently. Remember, each of the search we have to start from the root, right, and going down. In other words, these top levels have to be very fast to access in the search process. And we can store these top levels in the buffer instead. And now we have level 1, which will be stored in 1 page, about 8K bytes. Level 2 can be stored in 133 pages, about 1 megabyte. And level 3 can be stored in 70,000 pages, over 133 megabytes. So this is about some properties and the information for B+tree we can use for database systems. You don't have to memorize the numbers. You just need to know how to calculate the maximum numbers and how to calculate this node capacity for certain fan-out numbers. And with storage space, we can use in the buffer for storing the top levels. If you know how to calculate them, it should be very easy for you to understand these materials, right? Okay, so this is about B+tree. And in the next class, we will talk about the insertion, deletion, update of the B+tree in details. Okay, that's it for today. Thanks for your attention.